So we've seen linear functions, we've seen power laws, we've seen exponentials, and we've seen hyperbolas, all processes that head off to infinity at varying rates. And in this lecture we're going to consider processes that change over time but remain within certain bounds. So we're going to consider oscillations or cycles. So there is change, but it remains within certain limits. And specifically we're going to consider a type of oscillation known as a simple harmonic oscillator. And although this idea is useful for studying the cycles that we see in socio-historical processes, such as cycles in the economy, it's also useful for studying quantisation. So in history, there can only be a certain number of empires at a time. You can't have half an empire. So the number of empires will always increase or decrease by one. That is quantisation. You have a whole number of empires and you jump from one whole number to another. You don't increase smoothly up and down. And as we will see, the idea of cycles is useful as a model of quantisation. Quantisation can emerge naturally from the behaviour of this kind of system. So to start with, we just need to review our ideas of sine and cosine because these are going to prove extremely important in what we will be talking about. So here is a right-angled triangle, and this, the longest side, is the hypotenuse, which I've labelled R, and this angle we can label theta, Greek letter theta. Then the length of this side is R times sine theta, and the length of this side is R times cos theta, and cosine theta, cos theta. And this is just a definition of sine and cosine. And as I say, we will be using that now in our study of simple harmonic oscillators. So let's draw the circle here, and I'm going to put over here a chart in which the angle theta is going to vary, and in this circle the angle theta is going to be measured from this line, and we have that distance, which as we've just seen is r sine theta, the vertical distance to a point on the rim of the circle, and here is r cosine theta, the horizontal distance. And what I'm going to do on this chart is plot r times the sine of theta. Well, supposing we start with theta is 0, so, and it's going to increase as we go around the circle. Theta is going to grow. So we'll start with theta is 0. What is r sine theta? Well, it's 0. There's no vertical distance at all. When theta is 0, it's completely flat along this line. So there's no vertical distance. Then as we swing up in theta, the vertical distance is going to be increasing until we get to here and it's at a maximum. So when theta is 90 degrees, we're at the maximum. So I'll put that here. That's going to be 90 degrees, a quarter of a circle. And then as we keep going around, theta is still increasing. As we keep going around, now the vertical distance from this line here is decreasing again until we get back to 0. So we're going to end up there. And as we keep going round, so theta is now all the way around here, the vertical distance from the line is now in the negative direction. It's below the line, so it's negative. And it's going to keep getting more and more negative until we get to this point. That's 3/4 of the way around the circle, 270 degrees. That's as maximum negative. That's as far below the axis as it can get in the vertical direction. So we'll be somewhere over here. And now as we keep going round, the vertical distance here is decreasing again back to 0. So we'll put that there. And I've just picked out the sort of extreme points. And if we looked at how sine varied in between, we would get a curve that looks like this. And what you might see from this is that when theta is 0, when the angle is 0, the value of the vertical measurement, r sine theta, is increasing at a maximum rate, because the point on the end of the circle is heading directly upwards at this point. So it's increasing rapidly in the vertical direction. But as we get somewhere like here, the point is moving in this direction. So its movement in the vertical direction has diminished. So that's why the curve is sloping over here. Although theta is changing at the same rate, the vertical distance is increasing more slowly until we get to the top, when the rate of change of the vertical distance is now a minimum. So it is neither increasing nor decreasing. The rate of change is 0. So it's flattened off. And then as we come down the other side, the vertical distance is at first decreasing slowly, but then it becomes decreasing at a maximum here. So when we're going through this 0, because at this point the vertical distance is once again 0, but it's decreasing at its most rapid rate as it goes through this horizontal line. And then once again the vertical distance decreases slowly until there's no movement in the vertical direction. It's all horizontal at the low point. And that's again what we see, that it's very fast decreasing at first, but it turns over until it's not increasing or decreasing at this point. It's reached a minimum, but it's not going up or down. And then as we go beyond it, it starts to accelerate again, and then until it gets back to this point where it's once again moving at its most rapid. And this is a sine curve, or a sine wave. And now let's have a look at what's happening to the cosine. So I'll put that on this same chart, and we'll put it as our cosine of theta. Well, at this point where I said the sine was 0, the cosine is the maximum. It's the whole horizontal distance. So the cosine at theta 0 is a maximum. And then as we go up to here, the cosine is shrinking until at this point it is 0. There's no horizontal distance. So when the sine has reached a maximum, the cosine is 0. And then as we keep going round now, the cosine is becoming negative. The horizontal distance is in this direction until it reaches its maximum negative at this point. So the cosine part becomes maximum negative when the sine theta is at 0. And then we go through again, and now the horizontal distance is still negative in this direction, but it is becoming less and less negative as the distance is moving back towards 0, as it is at that point. There's no horizontal part. So we're back to 0 here. And then we keep going round. Now the horizontal part, the cosine, is positive in this direction, and it is increasing again to its maximum. So we're there. So again, if we join up the points, we've got something like that, which is just the same as the sine wave, but it is shifted along by, in fact, a quarter of a cycle. It's kind of a quarter of a cycle behind this one. So those are our sine and cosine waves. And we may notice that the maximum value here is just r. And if we had a circle of radius 1, then this would just be sine and cosine. So sine and cosine go between 1 and, because it would be 1 times sine theta, they go between 1 and minus 1, and they're 0 at that point. So here is something moving in a cycle, and this is the result when we look at how it goes up and down as theta changes. It's really just oscillating up and down, and we stretch it out in terms of theta, so we get this sine wave. So in a circle, as we know, we can measure the angle in degrees, and one full rotation is 360 degrees. So that's 0, 90, 180, 270, 360 degrees as the angle goes round. But another way of measuring angle is in terms of radians, and the definition of a radian is such that if this angle is 1 radian in a circle with radius r, then that distance along the circle is equal to r. That's a definition of a radian. 1 radian. And the degree divides a circle into 360 degrees. So we have, so it divides the circle into 360, so we have 360 degrees. How much does the radian divide the circle into? Well, we should know that the whole circumference of a circle is 2 pi times the radius. So there's 2 pi r divided by r, because that's the whole length, and we find out how many radians go into the whole length. Well, it's 2 pi r over r, so it's 2 pi. So a full revolution measured in radians is 2 pi. And the reason we use radians is because as we start to differentiate sines and cosines, it makes the mathematics a lot easier. And so we shall be exclusively using radians. So some things to remember: that 90 degrees is pi by 2. That's a half pi, because there are 4 lots of 90 degrees in a circle, and so 2 pi divided by 4 is pi by 2, half pi, and 180 degrees corresponds to pi, and then 270, 3 pi by 2, and 360 degrees is 2 pi. So I've drawn up here sine and cosine curves that go all the way up to 6 pi, and they could go on beyond that. So we don't need to think of the sine and cosine as coming to a halt at when theta is 2 pi, 360 degrees, a whole circle. We can think of it as carrying on around the circle, so that theta is continuing to increase, but it's now lapping itself. So it's covering the same ground. So as theta goes from 2 pi to 4 pi, it behaves in exactly the same way. And then the same as from 4 pi to 6 pi, the sine behaves in the same way, and ditto for the cosine. And so we can see that as theta keeps changing and keeps increasing, we've got an oscillation up and down, up and down, up and down, many times over in this direction. And we can also see that the sine wave or the cosine wave tends to divide this variation of theta up into chunks. There is a periodicity to it, a recurrence to it, and that is the roots of this idea of quantization that we'll be talking about later on. Okay, now supposing we have something that is moving around a circle, and let's say that it takes a time big T to go around the whole circle. We call that the period of the motion, of the oscillation, of the cycle. And then the number of revolutions per second, or per unit time more generally, is going to be equal to 1 divided by the period. That is how many cycles we can fit into 1 unit of time. And instead of saying revs, I'll say cycles more generally. So 1 divided by t is the number of cycles per unit time, and we call that the frequency. So we can write that the frequency f is equal to 1 over t. Now let's consider how the angle theta here depends upon time. So if it has a period of t, then the motion does 2 pi divided by t radians per unit time. Because it does 2 pi radians in a time t, which is the period. So that's 2 pi over t radians per unit of time. And therefore the angle theta is going to be the number of radians per unit time multiplied by the time. So that's how many radians it's doing per second, say. And so if it's 10 seconds, it will be 10 times that number of radians. And we call this the angular frequency, which we tend to write as the Greek letter omega, little omega. That's the angular frequency. So we can then just write theta equals omega t. The angular frequency, the number of radians per second times the time taken, gives you the total number of radians. And we can also see from this that t is equal to 2 pi over omega. Just rearrange that equation, swap omega and t. And because 1 over t is the frequency f, we could also say that omega equals 2 pi f. So those are just 3 different ways of writing the same thing. So if we now consider a variable that varies with the sine theta, which is this vertical distance which goes up, back to 0, down to its maximum negative, back to 0, and then just keeps repeating that. Let's say we'll write that y is equal to, and let's assume that the radius of the circle is a. So the maximum value of y is a, the minimum value of y is minus a. Y is equal to a times the sine of theta, just as we had before. And so y equals a sine omega t, because theta equals omega t. As time varies, that's how theta varies. So this is an equation that describes the motion of something that's oscillating in a cycle, as in this case in the vertical direction, up and down, up and down. And this is a simple harmonic oscillator, or SHO. So this is just one type of oscillation, and it's a very simple and it's a very regular kind of oscillation. And we could also have y equals a cosine omega t. That would also describe exactly the same kind of pattern of motion. It would be that way, but it's arbitrary what we think of as vertical and horizontal. And then to make it a little bit more general, if we don't start here at 0, but start at some existing angle, which let's say we'll call phi, Greek letter phi, then at time 0 it will already be at phi, and then it will move on from there. So finally the most general equation is going to be y equals a sine omega t plus phi. And then I said we could have y equals a cosine of omega t. That would be the equivalent of putting phi as pi by 2. So if this is 0, this is pi by 2 here, when the sine is a maximum. well, the cosine is a maximum when if this is time is 0. So when actually that's theta. So when theta is pi by 2, that is when the sine is the maximum. So if we add pi by 2 in here, we'll get sine of, if this is 0, sine of pi by 2. So that's why the cosine is a maximum. And then it proceeds from there. It's then just the same curve, just brought this way because we've added pi by 2 to everything. So this is completely general. It implies the cosine variation as well as the sine variation. So it's time to talk derivatives, and I'm just going to tell you what these are. So if we have sine of theta, then the derivative with respect to theta is cosine of theta. And if we have cosine of theta, the derivative with respect to theta is minus the sine of theta. Now, it's not too difficult to derive these, but it does require some other knowledge of properties of sines and cosines, so-called trigonometric identities, which we don't need to get bogged down in. We saw at the beginning of this lesson on calculus how we can work out the derivative from scratch in a particular case. So we have an understanding of the principles involved. We don't need to know the details of how each derivative is arrived at. We just want to use them in practice. And it's not too difficult to remember. Sine goes to cosine and cosine goes to minus sine. But we can get an intuitive feel for where these come from. So let's have a look at that. Okay, so I put up here a sine wave and superimposed on it a cosine wave. And if we look at the start here, when theta is 0, at this point the sine is increasing at its maximum rate. Later on it slows down. So this is where it is at a maximum. So we can say that the rate of change of the sine is here at its maximum positive value. And if we look at the value of cosine, it's at its maximum positive value. So the rate of change, in other words, the derivative of sine is maximum positive and cosine is maximum positive. So that supports this idea that the derivative of sine is equal to the cosine. And then we can have a look here at a quarter of a cycle, pi by 2. Here, the rate of change of sine is 0 because it's neither increasing nor decreasing. It's come to the top of its swing and it's just come to a halt and is about to start moving downwards. So the instantaneous rate of change is 0 and the cosine is at 0. And then here at pi radians, half a cycle, the sine is at, decreasing at its maximum rate. It's shooting through the theta axis. So here the rate of change is maximum negative and the cosine is at maximum negative. And then here again the sine is just, the rate of change is at 0. It's just come to a halt. It's neither increasing nor decreasing. So we can again write rate of change equals 0 and cosine is 0. So that certainly seems to support this idea. Wherever we look at what the rate of change of the sine is, it's the same as the value of the cosine. And let's do the same for the cosine. So for the cosine here, its rate of change is 0. It's just come to a halt. It's neither increasing nor decreasing. And the sine is 0. So I'll label these again, but we should recognise sine, and that's cosine. And then here, cosine is decreasing at its maximum rate. It's going down, and it's at its steepest slope that it gets to. So that there, the rate of change of cosine is maximum negative. And what's the value of sine at this point? Well, it is maximum positive. So that is in line with this equation. The rate of change of the cosine is the negative of the sine. It's the maximum, but it's maximum negative as opposed to maximum positive. And then let's continue here. The rate of change of cosine is 0, and the value of sine is 0. And lastly here, the rate of change of cosine is now shooting up at its maximum rate, so that's maximum positive, and sine is maximum negative. So again, the sine is the negative of the rate of change of cosine. So, you know, we've intuitively justified that by just taking a few points. And where it gets interesting then is if we differentiate this a second time. So let's start with our d by d theta of sine theta equals cosine of theta. And let's differentiate both sides a second time. So we're going to turn this into the second derivative, d2 by d theta squared of sine theta. That's d by d theta of d by d theta. And here we've got a d by d theta now. So we've got d by d theta of cos theta. And that equals, according to this, minus sine theta. So when we differentiate sine theta twice, we get minus sine theta. We get minus what we started with. And what about with cos theta? Well, we start with d by d theta of cos theta equals sine minus sine theta from that. And we're going to differentiate twice, so we've got d2 by d theta squared. This is minus sine theta, so it becomes minus d by d theta of sine theta. D by d theta sine theta is cos theta, so this is minus cos theta. So the same is true for cosine. If we start with cosine, differentiate it twice, we get minus cosine, so we get minus what we started with. And we can compare that with what happened with the exponential. With an exponential, if we have the expression y equals e to the x, then we know that dy by dx equals e to the x, which equals y. So with the exponential, dy by dx equals y. With the sine and cosine, so if we have, and I'll just take sine x, just take the sine as the example, but the same would apply to cosine. If we've got y equals sine x, then we know that d2y by dx squared equals, differentiate that twice, we get minus the sine of x, which in other words equals minus y. And we could differentiate exponential again twice. So if we got dy by dx equals y, we could also write this as d2y by differentiating again. d2y by dx squared equals y. So if we see that d2y by dx squared is minus y, we're going to have sine cosine, we're going to have an oscillation in y. If we see dy by dx equals y, or d2y by dx squared equals y, we're going to see exponential growth. Okay, let's just have a look at that again in the context of the differential equation. So our most general equation for something that oscillates with time, or a simple harmonic oscillator anyway, was y equals a times sine omega t plus phi. Phi was the starting angle. A is called the amplitude of the oscillation. And this phi, the starting angle, is typically known as the phase. So that's why we use phi for phase. And omega t, you should remember, is the angular frequency. Which is the number of radians per unit time. So let's now differentiate that using the rules that we've just seen for the derivatives of sine and cosine. Well, if we take the derivative with respect to time, which I'll write as y dot, then it's going to equal to a is just a constant multiplied by the derivative of this. And here we're going to have to use our chain rule. So we know what the derivative of sine t is. What's the derivative of sine omega t plus phi? Well, with the chain rule, we first treat that as the variable. So sine just goes to cosine. Sine theta goes to cosine of theta. So we're just treating that as the variable, keeping it as a chunk. But then we have to multiply by the derivative of the bracket, as we say. So we're differentiating with respect to time, so omega t becomes omega, phi is a constant, so that disappears. So we're just left with omega. So I'll write that out as a omega cosine omega t plus phi. And now we're going to differentiate again. Find y double dot. So we just do the same thing here, the chain rule. So cosine becomes minus sine, and then as we multiply by the derivative of the bracket, this again is just omega. So it will be minus a times another omega, so that becomes omega squared, and cosine, as I said, becomes now sine, or minus sine. So y double dot, if we start from that, is minus omega a omega squared sine omega t plus phi, and we can see from that that it's just equal to y with the extra factor of omega squared. So we can write y double dot equals minus omega squared y. And that is a sort of differential equation we might find, and we know that its solution is that. So if it were, for example, y double dot equals minus a constant k times y, then this k would correspond to the omega squared, or in other words, the angular frequency is the square root of k. Omega, this would have to be the square root of k. But because when we're dealing with equations of this kind, knowing that this is actually going to be the square of the angular frequency, we often just write the constant as something squared, typically omega squared. Yes, so any equation that's of the form where the second rate of change, the acceleration of y, is proportional to the negative of y, then that is going to give us oscillatory motion. And we can sort of or list that along with the other things we've found so far. So we know that if y dot equals a constant, then that means linear change, a linear law with time. If y dot equals well, proportional to, let's say, y, as I've just discussed, it gives us an exponential. If y dot is proportional to y squared, then we've got hyperbolic process with a singularity. And now we say if we've got y double dot is proportional to minus y, then we've got oscillation, or more strictly a simple harmonic oscillator, the sine oscillation. So here we've got a bit of a toolkit emerging for various kinds of dynamics that we might see in socio-historical processes, and then an understanding of the mathematical laws that must lie behind them. So we start to look for, if we see an oscillatory motion, we say, well, why is it that the second rate of change would be proportional to the negative of the value? And once we can understand why that is, then we've explained why it is an oscillatory motion. Okay, now I've written up here our basic differential equation, y double dot equals minus 1 omega squared y, which we know gives sinusoidal oscillations. In other words, it gives expressions for y like this, that y equals in general a sine omega t plus phi. And we've got that omega comes from the constant in front of y, or minus y, in this equation. But we've also got two constants, a and phi, the phase and the amplitude, which are not mentioned anywhere in this equation. So we've got to invent those. Well, these are our constants of integration, in effect. They will depend upon the initial conditions. And we've got two constants of integration because unlike the differential equations we've been seeing so far, this is what we'd call a second order differential equation. It's got y double dot and not just y dot. So y is differentiated twice. So to get back to y, we're going to have to integrate twice. And each integration is going to give us a constant of integration. So that's why we have two constants that we need to determine. And so we'll need to be given two initial conditions. We can be told what y is at time t equals 0, but that's not enough with just one equation to work out two constants. We'd also need to know something like the rate of change of y at time t equals 0. And with those two facts, we then get two equations, and we should be able to work out our a and phi. Okay, now I'd like to take another look at a comparison between the exponential function and the sine and cosine functions, because they are connected. So let's start with an exponential, y equals e to the omega t. And we know that if we differentiate this with respect to time, we're going to bring down the omega, so this becomes omega e to the omega t. And if we differentiate again, d2y by dt squared, we bring another omega down, so we get omega squared e to the omega t. And then that tells us that d2y by dt squared equals omega squared times what we started with, e to the omega t, so d2y by dt squared equals omega squared y. And this might remind us of what we saw with sines and cosines, where we had something like this, but there was a minus sign in front of it. And we might ask ourselves, well, is there something we could put in front here that we'll end up with a minus sign? So, we might, for example, try, well, what if we put minus omega t there? Well, this would then be minus omega here. but this would be minus omega squared. Now, the square of a negative number is a positive number. So we would end up, in fact, with a positive number, just omega squared. Minus omega squared is just omega squared. So we wouldn't get a negative sign. So we need something in front here that when we square it, gives us a negative. Well, if all numbers, whether they're positive or negative, square to a positive number, that's going to be a bit difficult. So what we do is we imagine a number that, when it is squared, gives a negative. Specifically, we take what is known as the imaginary unit, I, that's defined as I squared equals minus 1. Or in other words, I is the square root of minus 1. So we just imagine that number. It's an imaginary number. And the square roots of all other negative numbers can just be expressed in terms of I. So, for example, the square root of minus 4 is 2i. That would be 2 squared times I squared, 4 times minus 1, minus 4. So let's try that then. We've got now y equals e to the I omega t. If we differentiate this, dy by dt equals, with the constant in front of the t is now I omega, so bring that down, I omega e to the I omega t. And d2y by dt squared equals another I omega, so we're going to get I squared omega squared e to the I omega t. And as we've just said, by definition, I squared is minus 1. So that's minus 1 times omega squared, or in other words, minus omega squared. So in this case, we find d2y by dt squared equals minus omega squared y, which is what we found for sines and cosines. So this y equals e to the I omega t is in some way related to sines and cosines. It seems to be another way of expressing the sine and cosine behaviour. It leads to the same conclusion, that the second derivative is the negative of what you started with. And we can see from these two equations the difference in why this gives us exponential growth and this gives us oscillations. So with this one, we're saying that if a system has a starting point here, the further it moves away from it, the faster it is moving, accelerating away in the positive direction. So it's continuing to accelerate in the same direction away. So it's just getting faster and faster and faster in the same direction. So it will just shoot off to infinity. But in this case, if it starts here, the further away it gets from that starting point, the origin, the more it's accelerating back towards it. So it's come back to the origin, and then if it goes beyond that into the negative side, the acceleration turns positive, so it's coming again back to the origin. So wherever it is accelerating towards the origin. And that is why we get an oscillation rather than going off in one direction or another. And let's just consider what would happen if, instead of being the acceleration that's the negative of y, it's just the speed, the rate of change, just dy by dt. So if we had dy by dt equals minus y, what would that produce? Well, we know that if we've got, an expression dy by dt equals ky, the solution to that is y equals e to the kt, just from our rules that we've studied for differentiating exponentials. So in this case, k is minus 1, so we've got y equals e to the minus t. I just did, left out any constants just to keep it simple. So what does y equals e to the minus t look like? Well, we can plot that. is t, y. Well, if it were y equals e to the t, that would just be an exponential, and we know that, you know, shoots off to infinity like that. But this is e to the minus t, so it's 1 over e to the t. So as e to the t gets very large, 1 over e to the t gets very small. So e to the minus t looks something like this. It shrinks towards the time axis. It shrinks towards 0. It would, as this reaches infinity in infinite time, this will eventually reach 0 in infinite time. So what we see is that if we just have that the rate of change is proportional to the negative of y, we don't get an oscillation. We just get a decay towards the starting point. So it would move back towards the starting point, but more and more slowly, and eventually reach it. There would be no oscillation. For the oscillation, we need the second rate of change. So that's because with the acceleration being proportional to the negative of the distance from the starting point, it's speeding up all the way to the starting point. Speeding up. It's speeding up more slowly as it gets there, but it's still speeding up. So when it reaches, it's moving very fast in that direction. So it overshoots, it goes beyond it. And now the acceleration has turned round, it's in the opposite direction, back to the starting point. It's moving very fast, so it's accelerating back is effectively means braking, so it's slowing down until it eventually comes to a halt, and then it continues accelerating back, and it accelerates all the way back to the starting point. So again, when it reaches a starting point, it's moving very fast in the opposite direction, so it goes beyond it, and then it turns around again and comes back, and always when it reaches the starting point, it is moving very fast and overshoots. So with the acceleration, we will get, being proportional to the negative y, we will get oscillation, but not if it's just the rate of change proportional to the negative y. And so that's the point of this for theoretical historians, is that if we see oscillation in a socio-historical system, we are going to say to ourselves, well, the system must have some kind of equilibrium point, and there must be some principle that the further away it is from the equilibrium, the greater the acceleration back towards that equilibrium point. So we must ask ourselves, why is it accelerating back towards that equilibrium point rather than just moving back towards it? And if we can answer that, then we've understood why we have got oscillations. Okay, I've written up what is known as Euler's formula. E to the I theta is equal to cosine theta plus I sine theta. This is known as a complex number because it's got a real part and an imaginary part. Sine theta times the imaginary square root of minus 1 I. I'm not going to prove that. This is a very useful and important formula. Again, it's not too difficult to memorize. And just to show then how this works, we can say that d by d theta of e to the I theta is going to be, if we take this side, is just going to be I e to the I theta, because that's just our rule for differentiating an exponential. So I should have written that a bit further over, but differentiating that is I e to the I theta, and differentiating this side, cosine goes to minus sine theta, and I times sine theta goes to cosine theta. and I can just rearrange this. I'll put the I cosine theta at the front and the minus sine theta second, and that is equal to I times cosine of theta plus I sine theta. Because I times cosine theta is just I cosine theta, and I times I sine theta is minus sine theta, because I squared is minus 1. So you can see that differentiating this is equal to I times that, and indeed differentiating this gives I times the same thing. So this is consistent. And then if we do it again, d2 by d theta squared of e to the I theta, we're going to get I brought down again. So we're going to get, I'll just jump to minus e to the I theta, I times I squared minus 1. And if we differentiate this, we're going to get minus sine is going to become minus cosine of theta, plus I times cosine of theta is going to become minus I times the sine of theta, because cosine goes to minus sine. And that is equal to minus 1, let's say, times cosine of theta plus I sine theta. So again, if it's e to the I theta, we differentiate it twice, we should get a minus sign in front of it. We're saying that e to the I theta is equivalent to this, and indeed if we differentiate this twice, we end up with a minus sign in front of the same thing. So that does seem to confirm the idea that e to the I theta equals cos theta plus I sine theta. The two things seem to amount to the same thing, just as we claimed. And also notice here that if we, when we said we differentiated this expression, we multiplied it by I, as here and here. So in some sort of sense, this kind of differentiation is a bit like multiplying by the square root of minus 1 in some sort of strange sense, which I will just leave there. Now I'd like to take a break here because we've been talking about some abstract and difficult concepts: differentiation, sines and cosines, the square root of minus 1. But from what we've just seen, these are all connected, and we're really just talking about one thing, and it's quite a simple thing, which is this idea of oscillation and how it occurs when something is pulled back towards its starting point. So we're just saying that the pendulum swings because it has an equilibrium position, and the further it moves away from that equilibrium position, the more it is pulled back towards it. And similarly then, we're saying that in theoretical history, in socio-historical systems, when we see oscillations, it's because there is some equilibrium point for the system, and the more the system is moved away from that equilibrium, the more it is driven back towards it or pulled back towards it. So the mathematical paraphernalia makes it look complex and difficult, but the idea is really a simple one. And I think that's why the great mystics like Hildegard of Bingen can understand the rules of the universe in ways that modern physicists are just beginning to catch up with. It's because the rules of the universe are ultimately based on quite simple principles, and people like Hildegard can see clearly those simple principles through their own intuition. The rest of us need the mathematics to arrive at the same destination, but the more we work with the mathematics, the more we see the connections and the simplicity underlying it all. So I'm taking you through all this mathematics, and if you're not familiar with it, it's probably quite difficult to assimilate, especially the rate at which the information is coming. But I'm not taking you on a journey from simple things to complex things. I'm taking you on a journey from complexity and confusion to underlying simplicity. So I'm taking you from the complexity and confusion of the world and the socio-historical processes to the deep simplicity that underlies them. And as we work with this mathematics, that simplicity should increasingly reveal itself. But that doesn't mean it's easy. Even for someone like Hildegard, there's no shortcuts. She entered the nunnery when she was 9 years old, and she spent years on spiritual exercises and spiritual discipline to gain the insights that she did. And it's the same for us. Theoretical history isn't something trivial. It's something that requires effort, but that's what makes it worthwhile. So let's get on with the lecture. So let's have a look again at our equation y double dot equals minus omega squared y. We're going to ask, in what kind of systems would this equation arise? Well, sometimes we may go straight to such an equation. For example, in the case of the pendulum, we can say that when it's in the centre, its weight is being balanced by the pull of the string. But the further away we go from the centre, the less of its weight is being supported by the string. So more and more of its weight is tending to pull it back towards the centre. So that is why the further away it gets, the y measuring the angle of the swing, the further away it gets, the more it is accelerating back towards the centre. So we've kind of gone straight to that equation. But another way we can get to such an equation can involve two variables. So let's suppose that we have two variables x and y, where x dot is proportional to y. So I'll put x dot equals alpha y, and y dot is proportional to x. So I'll put beta minus beta x. So y dot is proportional to the negative of x. So what this is saying is that the larger y, the faster x increases, and the larger x, the faster y decreases because of the negative. And we could then solve these equations, or work with these equations to differentiate this again. We'll get x double dot equals alpha y dot, which equals what y dot is here minus beta x, so that will be minus alpha times beta x. And similarly here, y dot is minus beta x, so y double dot is going to be equal to minus beta times x dot, and x dot is alpha y, so we get minus alpha beta y. So we get for both x dot and y dot, we get x dot is minus omega squared x, and y double dot equals minus omega squared y, where omega squared is equal to alpha beta. So we can see from this that they're both going to show oscillatory behaviour. They're both going to be simple harmonic oscillators, obeying this equation for the simple harmonic oscillator. And what's more, they both have the same angular frequency of the oscillation, the omega squared here, which is alpha beta, the product of these two constants. And we might also see that x plays the role of sine and y plays the role of cosine, because if x plays the role of sine, when we differentiate sine, we get cosine. And if y is playing the role of cosine, we differentiate that, we remember we get minus sine. So that's correct. So if we plot x and y on a chart, we'll see that if x oscillates like this, then y is oscillating like a cosine, a quarter of a cycle ahead of it, because y reaches its maximum a quarter of a cycle before x, and then it starts falling a quarter of a cycle before x does, and so on. So this kind of situation where we have a pair of equations for two variables that are connected like this will give us oscillatory behaviour in both variables. And let's have a look at an example where that might occur. So let's suppose in a society we define the population pressure.
Population pressure is the ratio of the existing population to the maximum population that can be supported with the available resources.
And I'll use for that the symbol L, which stands for load, because some theoretical historians use that term load and that symbol. So I use that for population pressure. The extent to which the population is pressing upon the available resources. And we'll also define the happiness of the population. So meaning the well-being, the good mood. If happiness is low, people are more likely to show unrest. If happiness is high, they're content with their lot and the society will be peaceful. So H is a measure of happiness. And we could then argue for models that the population pressure is, let's just put proportional to, we'll avoid constants. The rate of change of population pressure is proportional to the happiness, because the happier people are, the more prepared they are to have children. The more they feel that they can afford children, so they're more likely to have children. And but by having children, that causes the population to increase, which will therefore cause the population pressure to increase. And at the same time, let's suppose that the happiness changes at a rate that is proportional to minus the population pressure. So the larger the population pressure, the faster the happiness decreases. So if there's a lot of population pressure, people will be poor, there won't be many resources to go around, so they will become increasingly unhappy. Happiness decreases. If population pressure decreases, then the happiness will increase. And well, we can see that those two equations are like the ones I just put up for x and y. If we differentiate that one again, we get L double dot equals H dot, well, that is proportional to H dot, which is proportional to minus L. So this is kind of Turchin's theory of cycles in population pressure and social unrest, kind of in a nutshell. And we can actually make it even neater and more compact by defining something I'll call psi, the Greek letter psi, and in fact that is a letter that's used in the structural demographic theory of cycles of population pressure and social unrest. So I'll call this psi and define it as H plus I times L. So again, I, the square root of minus 1. H happiness, L population pressure. And this is a complex number. It has a real part and an imaginary part, number multiplied by the imaginary square root of -1. And now if we say psi dot equals I psi, we can substitute in from here into this equation, and we'll see that psi dot is going to equal H plus IL dotted, so it will just be H dot and then L dot there, H dot plus IL dot. So it's taking the time derivative of those two. And from here, it should equal I psi. So it should, that we're saying that will equal I times H plus IL. And I times H plus IL is just IH plus I squared L, I times I. But I squared is -1. So we get IH minus L, which I can write as minus L plus IH. And now what we can see from here is that the real part of this, which is H dot, is equal to, it must be equal to the real part of that. We can only compare a real number with a real number and an imaginary number with an imaginary number. So H dot equals minus L, and L dot, which is the multiple of I here, equals H, which is the multiple of I there. So from this equation we get H dot must equal minus L and L dot must equal H, which is the pair of equations we had before. So by defining this, we can write down just one equation, psi dot equals I psi, instead of these two. So this is kind of a very super compact way of expressing the theory of demographic cycles and cycles in civil unrest. Of course, this gives a simple harmonic oscillator. It gives sine waves and cosine waves as a solution, whereas Turchin's actual theory doesn't predict simple regular sine wave like oscillations, and when we come to that in a later module, we'll see that in detail, but also in one of these lectures just coming up, we'll see another type of system that can produce oscillation that is not a simple harmonic oscillator and that is closer to the kind of thing that Turchin is doing. And I mention this really is more as a point of interest. It's not something that we will perhaps emphasize later in the course, but I think it is a useful thing that you can do and that might become useful in theoretical history in due course. We're now going to have a look at something called the wave equation. So we've been drawing diagrams looking like this with our sine waves. So that's the variable y changing in time, and the formula for that is, ignoring the phase, we just set it to 0, y equals a sine omega t. We're calling this a wave, but it's not really a wave. It's just describing something that's oscillating up and down in time. But we can have waves that have a spatial aspect to them, like the waves of the sea. There's an oscillation in space as well as in time. So let's draw something like that. Okay, so here is a spatial wave, like the wave of the sea, and the whole wave is moving in that direction. So this is really a wave that's moving in the x direction. So these crests move along. And if we look at a particular point on the wave, it's oscillating in time like before. It's just going up and down as the wave passes. But now if we take a snapshot of this, we also have a wave in space in the x direction. So it's going up and down as we move back and forwards in x. And we call this distance between two crests the wavelength, represented by the Greek letter L or lambda, L for length. And we also know that we have a period of the oscillation, which is, we wrote as t, and that's related to the omega by 2 pi over omega. Because the angular frequency, omega, is 2 pi over t, because it completes 2 pi radians. That's one cycle, one oscillation in time t. So the rate, the angular frequency, is 2 pi radians per amount of time t. Well, with this lambda, we can also define a similar quantity, because if we call this 0 here, then as x goes from 0 to lambda, it completes an oscillation of 2 pi radians, 360 degrees, one complete cycle. And so we can say that it does 2 pi radians per amount of distance lambda. We call that k, and it's known as the wave number. So to calculate the amount of oscillation that has happened in the x direction as we go along, it's k times x, because every lambda gives us 2 pi. So if x is 0, this times x would be 0. If x is lambda, one wavelength, this would be 2 pi. If x is 2 lambda, 2 wavelengths, that would be 2 pi over lambda times 2 lambda, which would be 4 pi, which is, in other words, 2 complete cycles. So we multiply that by x to get the amount of an oscillation that's been done, just as we multiply the time t by this omega to get the amount of an oscillation that's occurred in time. And the wave equation that, or the equation for a spatial wave, or a wave that has spatial and temporal aspects like this, is y equals a sine omega t plus k times x. So we can see here that if we keep x constant, then we ignore that. That just becomes like the phase that we had. You know, in this equation, we always said we could have omega t plus phi. So this becomes constant. Then all we've got is something that oscillates in time. So that's looking at a particular x, and we've just got a sine omega t. On the other hand, if we take a snapshot in time, so this is fixed, this is constant, and so this is like a phase, phi, then we've got something sine kx. So this is something that oscillates in x, and with this wave number x implying this wavelength lambda. So as I said, when x is 0, this would be 0. When x is lambda, this would be 2 pi. Lambda times 2 pi over lambda is 2 pi. So this would be one complete oscillation. So we put the two together, and that describes the movement in both directions, both time and space at once. Now, in fact, if we put a plus sign in there, it actually describes a wave that's moving to the left. And so sometimes it can be more common to sort of assume that the default one has a minus sign there, because that describes a wave moving to the right. All right, we've got this formula describing a wave that varies in both time and space. And this is for one that's moving to the right, so we've got a minus sign in there. Now, this equation is a solution to the wave equation. Or this expression is a solution to the wave equation, which looks like this. d2y by dt squared equals c squared d2y by dx squared. Only we've introduced this new symbol, a curly d. And this curly d represents partial differentiation. It means that when we've got something that depends upon two variables, as in this case y depends upon both time and x distance, then we can differentiate with respect to one or other at a time. So that's a partial differential. So just to give an example, if we've got something like u equals x squared y, then the partial differential of u with respect to x, du by dx, is equal to, we just treat y as though it's a constant. So we just differentiating with respect to x, so we've got 2x. And then we still, y is just a constant multiplier. Whereas if we take the partial differential with respect to y, now we treat x squared, or x as the constant. So we've just got x squared, and the derivative then of y is just 1, so we just get x squared. So that's all it means. We just take an expression that depends on two variables, and we can differentiate with respect to one or the other, treating the one that we're not differentiating with respect to as a constant. So that's what this means here, that if we differentiate y with respect to t, treating x as a constant, it will come out as c squared times if we differentiate y with respect to x, treating time t as a constant, or differentiate twice. And I'm not going to take that equation and derive this, though that can be done. I'm just going to show that indeed this equation satisfies that one. So let's have a look firstly at d2y by dt squared. So dy by dt is going to be a, and then applying our chain rule, this sine is going to become a cosine of what's in the brackets, omega t minus kx, and then we must multiply by the differential of the bracket. Well, we're differentiating with respect to time, so, and kx, we're saying x is a constant, so that disappears as a constant, and we're just left with differentiating with omega t with respect to time, which is omega. So I can move that omega round the front. And we've got that a omega cos omega t minus kx. And then, let's see if we can squeeze it in here, d2y by dt squared, second derivative. Well, we're going to have a omega again. The cosine now is going to become a minus sine, and then we multiply by the differential of the bracket, which is again omega, so we've got omega squared. Should have put that in there. So really this is the same as when we were differentiating a sine omega t plus phi. We just get it multiplied by omega squared. And that is equal to, if this is y, minus omega squared y. And now let's do the same for differentiation with respect to x. So we've got dy by dx. Well, we're differentiating this with respect to x. So the sine becomes a cosine. Omega t minus kx. And then we differentiate, then we multiply by the derivative of the bracket. Well, the omega t is constant because we're differentiating with respect to x, so that disappears, and we've got minus k times x, so this becomes times minus k, the derivative of the bracket, which we can put in front here, so this becomes minus a k cos omega t minus kx. And then differentiate again with respect to x. This is going to be, we've got at the moment minus ak. The cosine is going to go to a minus sine. So that's sine, and it's with minus sine. We've already got a minus there, so now it's a double negative, so that minus sign disappears. But we've still got, because we're doing our chain rule, we've got to multiply by the derivative of the bracket, which is times, as before, minus k. So minus k, we've got a minus sign, and k squared, which is equal to minus k squared y. And now we're saying that d2y by dt squared equals c squared times d2y by dx squared. Well, we've got here for d2y by dt squared minus omega squared y. So we've got minus omega squared y. And we're saying that is equal to c squared times d2y by dx squared. Well, d2y by dx squared is minus k squared y. So that's c squared times minus k squared y. Or in other words, minus c squared k squared y. We're saying these two are equal. Well, we can get rid of the y's on both sides. Can get rid of the minus sign on both sides. So we're down to omega squared equals c squared k squared. Or in other words, c squared equals omega squared over k squared. Or in other words, c equals omega over k. So what we've shown is that this expression here satisfies this equation where c equals omega over k. So provided c equals omega over k. Or in other words, if we've got this expression of this formula, this equation, then that will satisfy it such that omega over k equals c. And now let's just have a little closer look at this. C equals omega over k. You should remember that omega is 2 pi f, where f is the frequency of the oscillation, and k was 2 pi over lambda. So this becomes the 2 pi's on the top and bottom cancel. We've got f divided by 1 over lambda, so it becomes just lambda on the top. So we get c equals f lambda. And it turns out that this c is the speed of the wave.
Frequency times wavelength is the number of wavelengths passing per unit time. In other words, the speed of the wave.
You know, I'm not deriving any of this rigorously. I'm just telling you that if you see this equation, then it has that solution. And this is something we may meet later on then, or will meet later on in some of the theories, that we'll find equations like this, and we now know that it's an expression like that that will satisfy them. And this omega and k are related to the speed of the propagation of the wave. And now, one last thing on the wave equation is that I've been talking about, you know, real waves oscillating in time and moving in space, like the waves of the sea, just for our intuition. But the variables that we're concerned with don't need to be spatial and temporal dimensions. There could be waves in other variables. And just to sort of emphasize that point, I'm going to give an example. It's you know, not necessarily a very realistic example, but we could imagine that the happiness of people is a function of, depends upon 2 things: their wealth, and I'll put their political orientation, P. Wealth, political orientation. And we could possibly imagine then a wave equation for these. We might sort of, after investigating how these things behave, we might find that they should be related by something like that. That the second derivative with respect to wealth is a constant multiple of the second derivative with respect to political orientation. We might find that, let's say, just to imagine. Then we would know that this satisfies an equation of the form h equals a sine omega w minus k p. Again, p is political orientation, w is wealth, and omega and k are the frequencies of the oscillations in those 2 variables, and they're related to c squared, as we've seen, by c equals omega over k. And so what that might mean then is that if we had such a population and we were looking at its happiness in the wealth dimension, we might see kind of a wave, so that the happiness is highest for poorer people. The people with middle incomes maybe become less happy because they've got something to lose, so they're kind of anxious about that. But they're not so wealthy that they don't fear what might happen if their wealth decreased. So they're kind of the most unhappy. They're working very hard. They're worried about slipping back here. They're aspiring to this. Whereas the very wealthy are happy because, you know, they've obviously got a lot of wealth and can control a lot of things. So so there's a wave in the wealth dimension, and then we might similarly have a wave in political orientation, so that, let's say, at a a low value of wealth, it looks something like this. People who are at extremes, despite having poor wealth, can be happy, maybe because they're kind of very motivated, politically motivated. So this is where wealth is low. So we're looking somewhere down here. There's a wave like that. And then when we go to middling wealth, because of this, the wealth curve is, there's also an oscillation in the wealth curve. So it varies in the political dimension, but also varies in the wealth dimension, so that the variation in the political dimension will look different. It's like the wave is passing through. You know, if we're looking at a particular different, this is a particular point in time, and then this is a different point in time, because the wave passes through, we get see a different part of the wave. So people who are middling wealth, if they're politically extreme, either political extreme, then they're particularly unhappy with their wealth. But people who are, you know, not politically oriented or very middling might be more happy with their wealth. That's, as I say, just a kind of imaginary example, and it may not make an awful lot of sense, but it's just to emphasize the point that we're not necessarily talking about waves in physical space and time when we're dealing with socio-historical systems and looking at socio-historical variables. Now, the reason for mentioning the wave equation is that waves lead to the idea of quantization. And the classic example is a stretched guitar string. So let's try and draw that. Here's a guitar string stretched between two supports. So it's fixed at the ends, and it's being plucked, and it's vibrating up and down. So at any particular point there is an oscillation in time, but there's also a spatial oscillation. This is part of a wave. You know, it would continue along like that. So in fact this is half of a wave, because we know from our sine waves that it goes from 0 to its maximum and back to 0, and then it goes to its minimum, negative maximum, and back to 0. So this is half a wavelength here. So if we say the length of the guitar string is L, then we can write down the wavelength here. It is equal to 2L, because this is half a wavelength, so the whole wavelength would be 2L. And let's also remember our formula for waves, that the speed of the wave is equal to the frequency times the wavelength. Well, I'll just state it as a fact, but you know, it can be shown that the speed of the wave just depends upon the tension and the density of the string, which isn't changing, so that's constant. So we can write that F equals C over lambda. So F, the frequency, will be C divided by this. So it's a half C over L. That's C divided by 2L. Now, this isn't the only way. Well, I don't know if I emphasised, but we know that it has to be at 0 here and here. The string at the end cannot vibrate up and down, you know, because it's fixed there. That's where it's attached to the support. So that has to be 0. And any other wave shape we draw in here to represent the vibration of the string also has to be 0 at the ends. So let's see how another way we could draw a wave between these two that's 0 at the end? Well, it would be just one wave from 0 to 0. And in this case, that's one wavelength. So the wavelength is just the length L. And the frequency is C over lambda. So that's just C over L. And let's have another look at another wave that we could fit in here to be 0 at the ends. Well, it would go like that. So that is now 1.5 wavelengths fitted into L. So this is 2/3 of L is the wavelength, because that's 1/3, 2/3, and 3/3 is the whole L. So the wavelength is 2/3. And so the frequency is going to be C divided by that. So it turns out to be 3/2 of C upon L. Let's just do one more. This time we can go like that and fit 2 whole wavelengths into the distance, but it's still 0 at the ends always. This just doesn't oscillate here. So in this case, we've got the wavelength is equal to 1/2 of L, because there are 2 wavelengths in L. So when we take C divided by 1/2 L, we'll get 2 C upon L. And then if we call this the fundamental frequency, as it is known, so F again, if we call this the fundamental frequency, then this is double that, because that's 1/2, this is the whole, so this is twice the fundamental frequency. And this is 3/2 of CL, so this is 3 times the fundamental frequency. And this is 4 times that. 4 times 1/2 is 2. And you can see the way this is going to go, that we'll have 5, 6 and so on times the fundamental frequency. So this is the fundamental frequency, and these are known as the harmonics, first, second, third harmonic, etc. And we can see that there is quantization in the frequencies that we can get. They're always a whole number multiple of the basic frequency. And the physicist Niels Bohr recognized this as a possible explanation for the quantization that is seen in the frequency of light emitted by atoms. He suggested that it's similar to a guitar string. You have to fit a certain number of wavelengths into the orbit of the electron around the nucleus. So if we imagine here's the nucleus of the atom, there's an electron orbiting. Well, if we start our wave there, the wave might go something like this, you know, trying to sort of make a wave that's connected round in a circle, and it has to come back to 0 here, because if that describes the way that electron is kind of oscillating in the atom, it has to join up, because it's either not moving or moving here, but it can't be both. So if it's not moving, then it has to join up. And so he suggested that because you then have to fit a whole number of waves in order to make it join up, it's going to be like this. The frequencies of light emitted from the atom will be in this situation of a fundamental and then multiples of that, which is what is actually found by experiment. So he had an explanation for it in terms of this kind of waves. So so the point is that he realized that the waves give rise to quantization, and that is what is used is the basis of quantum mechanics, also known as wave mechanics. And you may have also heard of Schrödinger's wave or Schrödinger's wave equation, which is used in quantum mechanics. So waves and quantization are fundamentally related, and that's very much the basis of quantum mechanics. Well, the same then could apply in theoretical history, where we also see quantization. For example, the sizes of empires show quantization through time, that for a long time empires were of a certain size. Empires came and went, but the average size of an empire didn't change. But then, after about 1,000 years, there was a sudden jump up, and now, as empires formed, they were much larger than they had been. But now they were all tended to be of that new typical size. And that went on for 1,000 years. And then there was another jump up to a new typical large size of empire. So instead of through history, us seeing empires gradually increasing in size, what we see is a long time when they were this size, and then a jump, and then a long time when they're this size, and then a jump. So there's quantization. And because the waves give rise to quantization, maybe we can develop some explanation for that using this idea of waves. And therefore maybe we can develop an equation that looks something like this. The wave equation. If we can show that the sizes of empires is described by some equation like that, then that could explain why they're quantized, because the solution to that is a wave, and we know that waves can be quantized like this and give us only a certain number of solutions, only a certain number of different frequencies of possible waves that we could have. So that is to some extent speculation, but we will see later in the course how we could possibly construct such an equation to explain quantizations. Okay, and the last idea that I'm going to talk about with relation to waves and oscillations is the idea of seasonality, or the way that waves have seasons. So here's some variable y that has an oscillation, a sine wave in time. We can divide this up into 4 distinctive seasons. At least this is one way of looking at it. That in this part of the wave, it's positive. The value of y is above the x-axis, so it's positive. And it's increasing. Y is increasing up to its maximum. Then in this part, this quarter of the wave, it's positive again. Y is always positive, but it's decreasing. Y is coming back down. Here, now, y is negative. It's below the x-axis, as below the time axis. And it's decreasing. And then lastly here, it's negative, but it is increasing now from its maximum negative back towards 0. And we could label these as perhaps summer, autumn, winter, and spring. So summer is warm and getting warmer. Autumn is warm and getting cooler. Winter is cool and getting colder. Spring is cool and getting warmer again. So that's one way of dividing up a wave into seasons, and it means that if we have a periodic oscillation in history, we can perhaps see it in terms of these 4 phases. And I'm just going to suggest another way we could apply the phases to the wave. So let's do it again here. This time we could divide it up more like this. This time we'd consider the summer, the time when it's all warm. And here it's not changing very much. Around the top of the curve, it's slowly changing. It's slowly increasing and slowly decreasing again. So this point, it's sort of warm and mostly staying fairly warm. So that's summer. You know, at least if we're thinking of heat up in this direction. And this is kind of our summer, when it's all positive and it's loitering around the positive area. And then here it's more rapidly decreasing, it's falling, and it's getting colder. So this is fall, as Americans would call it, or autumn. So it's decreasing down to its minimum, and it's rapidly changing at this point. And then we get another period now where it's kind of all negative, and it's loitering in this negative area down well below the axis. So this is our winter, when things are kind of negative and staying negative. And then it's increasing, becoming positive again, and it's doing that rapidly. So this is a time of rapid change. That's the spring. And this is indeed a bit like the way the heat varies through the year and how we label things. So this is the summer solstice, when the sun is kind of stops moving because it moves to us in the northern hemisphere. The sun moves north and the days get warmer, and it then reaches its solstice, its stationary point, and then starts moving back again. But so this is the solstice here, when the sun stops moving up and starts turning back down. This is the equinox, when day and night are equal, and the days are changing most rapidly. And then this is the winter solstice, when it's again furthest south from the perspective of us in the northern hemisphere, and it kind of stays there for a long time and kind of but stops retreating and gradually starts to come back up. And then the spring equinox, when the days are changing rapidly again. So we'll see that these ideas of different seasons can be used, for example, in Oswald Spengler's theory of civilization, or in cycles in generational attitudes, for example. Now, one last thing to mention is if we go back to our original definitions of sine and cosine, so that's theta there, this is the hypotenuse r, we said this is r sine theta, and that's r cos theta. And if we take a triangle where that is 1, and this is just sine theta and cos theta, then applying Pythagoras' theorem, the square on the hypotenuse, which is here 1 squared, is equal to the sum of the squares on the other 2 sides. So that's sine theta squared, or sine squared theta, and it's plus cos theta squared, cos squared theta as we write it. And this is a very important equation, which we can write the other way around too. Sine squared theta plus cos squared theta equals 1, which is a constant. So even though theta is varying, if we add sine squared to cos squared, it doesn't change. The value is just 1. It's just a constant. So let's just have a look at how that works. If we've got say, our sine wave there, we know it goes positive and negative, but when we square it, it'll only be positive. So it will look something like this. It goes up to that peak there, and then it comes down to 0. Instead of going, though, negative, it increases positively again, because this is squaring a negative number, and it looks like that. So that is sine squared theta, if this is sine theta. And then if we can put sine and cosine on the same graph, so we're going to have sine squared looking something like that, and cosine squared, remember it starts at 1 when sine is 0, and when sine has increased to its maximum 1 at pi by 2, 90 degrees, cosine has come down to 0. It's not going to continue. It's just like this. It's going to go positive again as it increases again. So cosine is going to look something like that, meant to be the same height. So it kind of swings opposite to the sine. Sine squared and cosine squared. And as we said, when you add the sine squared and the cosine squared, it will just come to a constant value, constant 1, when you add the two together. So as sine squared increases, cosine squared decreases, and then they swing opposite to each other. So when we have things like this in physics, it's often about energy switching between two modes. In a pendulum, for example, the pendulum comes to a halt there, but it is at its maximum height, so he says it's got the most potential energy. And then when it loses its potential energy, it comes down to the middle. At this point, it's got the most kinetic energy. It's moving fast, the fastest, and kinetic means kinetic energy is energy of movement. And then the kinetic energy decreases as it slows down, but it rises and it's got more potential energy, the potential to fall back down. So as the pendulum is swinging, the energy is switching constantly between the potential and the kinetic. Well, we might have things like that in social systems, that there might be some kind of energy that swings back and forth between two modes. And so this kind of principle that the sine squared plus cosine squared is constant might then be applicable in such situations.